These are the notes on the universe, which is a pretty ambitious scale to do notes about, but I will primarily be concerned with the early development of the universe, or what we know about that. So the universe. The universe is everything that we can observe. So not just everything that we do observe, but I guess anything that we could observe potentially. So it's really pretty much everything. It might make you wonder, well, what would there be beyond that, beyond the universe? Well, there are concepts beyond the universe, but none of them have been substantiated. They call it the multiverse concept and so on. But the universe is pretty much everything we're aware of. So it's really the biggest scale that we have. The word universe, the origin of the word, comes from Latin, universum, okay, which basically comes from turned into one. It meant the same thing to them as it does to us, essentially. They weren't aware how big it was back then in the Roman days, but it's pretty much the whole world, everything. The Big Bang is the earliest event we are aware of in our universe, the earliest thing that we still have any information for in our universe. The best we can do at estimating the date of the Big Bang is placing it around 13.8 billion years ago. And to understand what that number means, you might want to write it out, take a look at it, how many digits that has, 13.8 billion years ago. And it was a violent explosion that occurred, throwing material out in all directions. You might wonder how we could possibly know what happened 13.8 billion years ago when we sometimes have trouble reconstructing what happened a few centuries ago in history. There's some things we aren't clear about that happened way more recently. So the Big Bang. Well, the term the Big Bang was actually originally made to make fun of the theory. When the theory was first introduced, when they started finding evidence to suggest this might have happened, people were making fun of it. And that's where that term came from. Then scientists started using it legitimately in an unironic way, and that's the term that many people use today. Okay? The only problem with that term is the Big Bang was not big. In fact, it was so small, it was essentially a singularity, the smallest thing you could possibly have. And the word bang implies a sound. Well, you need certain things to have sound. You need matter to have sound. And it turns out that that was not present at the moment of the Big Bang. So I thought of another term for it. It might not be as catchy, but it's a little more descriptive. You could call it the small silence. I don't think that's catching on, but it would actually describe it better because it did not make noise and it wasn't big, not at all, very small. So how do we know about this event 13.8 billion years ago when we are so far down the line in history? Well, there's a lot of evidence for the Big Bang. I'm going to emphasize two pieces of evidence. There's actually more than this. But one of the primary reasons, the original reason that they came up with this concept was the red shift of galaxies. So we'll be discussing that a little bit later. The red shifts of galaxies definitely supports that the universe was smaller, for sure. And if you trace it back far enough, it puts everything back in one position, in one place, which is actually what originally gave rise to this concept. The second piece of evidence that I want to talk about that is also in the textbook is what we call cosmic background radiation. Cosmic background radiation is the leftover energy from the Big Bang. This energy keeps intergalactic space a few degrees, about 3 if you go by the Kelvin scale, above absolute zero. So if you were to go way out into space, if you could travel that far, get away from stars and galaxies, get away from everything you could, as far away as you could you would still find that the temperature wasn't as cold as it could get. It wouldn't be absolute zero. You're just a few degrees above it, 3 degrees. Now that doesn't sound like much. That doesn't sound like a lot. But if you imagine that the entire universe is still at 3 degrees Kelvin, well, that's a whole lot of energy that must have come from somewhere. That energy is the leftover energy from the Big Bang. It's just got very spread out, spread very, very thin. So what's an easier way to describe the cosmic background radiation? You could say that the cosmic background radiation means that the universe has not completely cooled off yet. If the universe had been around for, let's say, hundreds of billions of years instead of 13.8 billion, or let's say trillions of years, or let's say the universe had always been this size, well, then there's no way to get that much energy spread out around the universe. Everything would have cooled off to absolute zero, at least in intergalactic space. So the textbook goes into this quite a bit, and we'll discuss this again later. That is a major piece of evidence for the Big Bang. After the Big Bang, there was a period of rapid expansion. This is known as inflation. Like imagine if you have a balloon and you just bought the balloon and then you blow up the balloon. You inflate it, make it grow bigger. Now the period of inflation is usually differentiated from the rest of the history of the universe because it was such a rapid expansion and it happened over such a brief period of time, much, much less than even 1 second. Following that, the universe has continued to expand right up until this day, but not at the same rate it did for that initial moment after the Big Bang. There were a lot of interesting things going on in that early period when the universe was very young, and it caused the universe to have a very, very dramatic expansion. Because we're talking about an expanding explosion, it should not be a surprise that the structure of the universe resembles an expanding explosion. Explosions often have shock waves, which cause them to have characteristic shapes. This picture is of fireworks, so that's a little different. That's a well-organized one. Here's another one that's a little bit better. You can sort of see how some matter is concentrated in certain areas and there's gaps in between. Well, when we mapped the structure of our universe, it turned out that it had a structure with filaments very, very similar to what you would see after a small-scale explosion. Once they got this mapped in higher and higher detail and resolution, they noticed that it sort of resembled an old spider web, the kind of spider web we call a cobweb, where the structure isn't so neat and perfect anymore. The strands are breaking. Kind of looks like a web of a sort, a cobweb. So we call this structure web structure. What does that mean? That means in some places you've got concentrated matter. In other places you've got empty space, empty areas. So the matter in the universe isn't just spread out evenly, okay, at a constant rate, at a constant concentration. It's concentrated, it's clumped together in some areas. And that's partially due to the initial explosion and the rapid expansion afterwards, which established this web structure that the universe still has to this day. It's a good thing that we have a web structure, because if matter was spread out evenly, then we wouldn't have many of the things we have in our universe. Probably wouldn't even have galaxies if the matter was too spread out. After the Big Bang, there was a period where the universe was opaque, that light couldn't really travel through it. And so there's kind of a limit to how far back we can see directly. And the textbook does a good job of describing and illustrating why this was the case. So I would refer you to the diagrams in the textbook. They're actually the best ones I've seen to describe this process. And then the clumpy structure of the universe, the web structure of the universe, well, each of those clumps kind of led to a group of galaxies, and then those galaxies in turn formed the stars, and then around the stars we've got planets like here on Earth. So really, it's a good thing that the universe was formed in this way with this clumpy structure, this web structure. The early universe, and by the way, we are seeing kind of an image of the early universe, a low resolution image, when we look at the cosmic background radiation, was made of pretty much only two different elements, hydrogen and helium. Hydrogen and helium are the only two elements that are capable of forming outside of a star. And even for helium to form outside of a star, you need kind of extreme conditions like we had right after the Big Bang. So mostly the universe was made of hydrogen. Now, it might be a little misleading when they talk about by mass. If you talk about by mass, well, you would say hydrogen made up 3/4 of the universe. But that's because hydrogen is a very lightweight atom, and helium is 4 times the mass of it. So that weighs in favor of helium. If you talk about the number of atoms, hydrogen in the early universe made up well over 90%, 9 out of 10. And even to this day, it's about that same amount, just a little bit lower. It's still around 90% of the atoms in the universe are hydrogen. If you want to picture what these look like, hydrogen and helium, well, pretty much any nebula, any cloud in space is made of hydrogen and helium primarily. And then it's got little flecks of the other elements. So that cloud right there in the image, or pretty much any nebula that you're likely to see a picture of, is made up of hydrogen and helium. You wouldn't notice them, they would be dark, except for they're heated up until they're glowing. So what you're seeing is a glowing emission nebula here. Otherwise, it would just be a black cloud in space, and you'd only be able to tell if it was blocking out whatever stars were behind it. But what is going to determine the future of our universe has a lot to do with gravity, also known as universal gravitation. Gravity was quote unquote discovered by Isaac Newton. Well, actually, people had been experimenting with it before then, obviously, like Galileo and just anyone who ever dropped something, I guess. It was just Isaac Newton that connected the gravity we feel here on Earth to the gravity between the Earth and the Moon, and between the Earth and the Sun, and between any object. He realized that it was all the same thing. He formulated his famous equation that we are going to use in our new assignment, and it is F, which is the force of gravity, is equal to G, the big G, which is the universal gravitational constant, multiplied by the two masses. The two objects, the mass of each object multiplied together and divided by the distance between them squared. Now that is important. Because gravity diminishes, it's divided by the distance between the objects squared. So when objects get twice as far apart, the gravity doesn't divide by 2, it divides by 2 squared, it divides by 4. When objects move 10 times farther apart, you don't divide the force of gravity by 10, you divide it by 10 squared, which is 100. So gravity is very concentrated near the object and it drops away rapidly. However, it does extend, theoretically, forever. There is no limit to the extent of the gravitational force, although eventually it gets very, very, very weak, very minor. So gravitational force decreases with the greater distance. The farther away you are, the weaker it is. It depends on the mass of the object. The greater the mass of an object, the greater its gravitational force. So a lot of people think because everything falls at the same acceleration here on Earth that everything is feeling the same force of gravity. No, that is not true. A larger, more massive object does experience a greater force of gravity. The only problem is it's harder to move a more massive object. It has more inertia. So that exactly compensates for that. And that's why everything falls at the same rate in, let's say, Earth's gravitational field. So a more massive object does experience a greater force of gravity. Now, at the bottom, it says, note, Einstein later showed in general relativity that gravitation is caused by the warping of space around masses. How did he prove this? He proved this by things that would only happen if the space itself was warped, and it wasn't just a gravitational attraction, a force between two objects. He showed that even light was affected by gravitational impressions in the universe. So light should not be affected by gravity under this equation because light has no mass. But Einstein shows that it did. So there are a few things that this equation won't get you through, but for the most part, it's pretty good at predicting the force of gravity between any two objects, as long as you know the mass of each object and the distance between them. So let's take a closer look at Newton's equation for universal gravitation. F, which is the force of gravity, is equal to the universal gravitational constant, the big G, multiplied by the mass of one object times the mass of the second object, divided by the distance between them squared, r squared. The gravitational constant, the big G, is 6.674 times 10 to the negative 11 meters cubed per kilogram second squared. Now, is that a big number or a small number? It is a small number. So small numbers don't usually make much difference unless they are multiplied in. If you were adding a small number like that, it wouldn't make much difference, but we are multiplying it in, so it has a huge effect. What is a meter cubed per kilogram second squared? I wouldn't boggle your mind with that. It's just one of those things that constants get. Constants get weird units, and that's because those units are designed to cancel out when you get your final answer. So when you get your final answer, well, those units should make sense. The units of force you will get over there will be in newtons, but in the meantime, you're going to have weird units along the way. So what's going to happen to our universe? We've known for a long time that there were really only two options for the future of the universe. There's really only two possible paths. One is that the universe will just expand forever, just keep on expanding and expanding and expanding, and eventually what will happen is we will no longer even see other galaxies, and the universe will cool off, and they call that the thermodynamic death of the universe. It sounds kind of sad, but don't worry, it would take a very long time, something like 100 billion years, so I wouldn't worry too much about that future. The other option is, though, what if there is enough gravity? What if there's enough mass in the universe and they're still close enough together, the masses are still close enough to each other that there's enough gravity between them to actually slow this expansion? If that were to happen, it turns out there is no possibility that the universe could just stop expanding and stay like that, because gravity would continue to pull the galaxies, any masses, closer together. And then they would get closer together, gravity would increase. As they got closer, it would accelerate. They would be pulled in faster and faster, and then they would collapse. And that is what we call the Big Crunch. That has been hypothesized for many years as sort of the exact opposite of the Big Bang. And yes, again, it has a funny name, the Big Crunch. But now, guess what? The evidence has rolled in, and over the past decade, we've pretty much figured out which option is going to happen. We know how much mass there is in the universe, even though we don't know what all of it really is. There's what we call dark matter, but we can still measure its mass. And based on what we know now, it's almost, I would say almost decisive that option number 1 is what we can expect for the future of our universe. The universe will expand forever. Because not only is the universe not slowing down enough to ever stop expanding and collapse, no, not only that, it's actually accelerating its expansion again. And we're not sure why. They call this dark energy. Whatever is making the universe inflate again, so to speak, not quite as dramatic percentage-wise as the original inflation we talked about right after the Big Bang, but it is accelerating. The universe is now expanding faster and faster. So that clearly means that gravity is not doing its job. There's not going to be enough gravity to slow it down and stop it if it's actually speeding up. So it's pretty much known, not 100%, but evidence is stacking up that the universe will expand forever and never collapse. Now, I want to leave off today with a couple of analogies. Now, these are concepts that are difficult for us to understand in a straightforward way. So we often need to understand concepts like this using an analogy. Okay, so the analogy here is to try to understand sort of the geometry of the universe. A lot of people think you could draw the universe. Physicists often do this. They draw a little circle and say, boom, that's your universe. But actually, it's almost impossible to draw what the universe would look like. It's almost like something that we can't conceive with our mind. But there is a way to represent the way the universe behaves by analogy, by taking away one dimension. If we take away one dimension, instead of dealing with a three-dimensional universe of space, how about a 2D universe, sort of a flat universe? Okay, on the bottom, you can see that there's sort of like a rectangular flat, like a sheet of paper, and it's limited. It's only got so much area, surface area. So of course, if you only have so much surface area, if you travel far enough, you will eventually reach an edge. That's what we're used to on a piece of paper, right? And you could bend that paper, fold it up, change it into different shapes like the saddle, the one in the middle. And notice how that changes the geometry of that triangle that's on it. But even though you've bent it a bit, you can still eventually reach an edge. Although the path you follow, notice, has been bent. Okay? So what's the analogy? Well, space is warped. Einstein showed us that space is bent around matter. Now, what about the one on the top? Now, by the way, the two lower ones are obviously limited in area. There's only so many little squares that are on that surface. So it's what we call a finite area, right? And then we've got the ball on top, the sphere, kind of like the Earth, like a globe, right? Well, a sphere has a finite area as well. You could check off all of those boxes that are on there, go around the entire thing, and eventually you'd have checked them all. So it's not like a sphere has unlimited area. There's only so much surface on the Earth, for example, right? But think about this. Couldn't you travel on that sphere as far as you want, keep going and going, and never reach an end? So even though that sphere has finite area, you never reach a boundary. You never reach an end to it, an edge. So when we talk about the universe being infinite, well, that means it doesn't have a boundary. You can't say, oh, I'm going to put my finger right there. That's the edge of the universe. There actually is no such place. Not only that, there's nowhere in the universe that is even closer to the edge of the universe. Anywhere you are feels like you're in the middle of the universe, just like we do ourselves, just like the ancient Greeks did. It just seems like we're in the middle. And you might as well say that we are, because anywhere in the universe feels like the middle of the universe. But that does not necessarily mean that the universe has infinite volume. Because space is warped, you don't sort of travel in straight lines. You don't really get any progress towards the edge, towards a boundary. you could just keep going and going through the universe. So you could keep traveling and traveling through the universe. You never get to an edge. You never even get any closer to an edge. Just like you could keep going on that sphere and you never get any closer to the end of the surface of that sphere. This is a great analogy for understanding the universe, and try picturing that. Add one more dimension, and if you can do it, well, good luck. Okay, if you can handle that, that's a very tricky concept. Add one more dimension to that. So space is warped and there is no boundary to the universe. So in a certain sense, it is infinite, okay, but it can still be finite in volume. The second analogy is what we call Hubble's law. Well, Hubble's law was discovered by the great astronomer Edwin Hubble. He noticed that galaxies seem to be moving away from us, pretty much all of them, not all of them, most of them moving away from us. And he came up with this idea that, well, if all the galaxies are moving away from us, if you were on one of those other galaxies, it would appear like all the other galaxies are moving away from you. And sometimes we use the balloon analogy, like they do in the textbook. The balloon analogy sort of describes this. A better analogy, harder to replicate in an experiment though, but easy to think about, is raisin bread dough. So to help picture the expanding universe, imagine a loaf of raisin bread dough. Now, if you're familiar with bread dough, it starts off small, and then the yeast eats up the sugar, making little carbon dioxide bubbles, causing it to swell up and expand. This would be before you throw the bread in the oven, okay, to make it, give it a hard surface, and before you would eat it, of course. So while the dough is rising, it's behaving very much like our universe. Raisins that are located farther apart will move away from each other more rapidly than raisins that are near each other. So notice that it says the raisin bread dough before it rises, the raisin bread dough a few hours later. Notice that those raisins that are 2 centimeters apart in the first image are now 6 centimeters apart, let's say 2 hours later. Well, they've moved 4 centimeters in 2 hours. That's 2 centimeters per hour, right? Then we've got these other raisins that are 5 centimeters apart. Well, during that period of time, 2 hours, let's say, they've expanded. Now they're 15 centimeters apart. Interesting, okay? Now, both of them have tripled the amount of distance between, but the speed that they've moved is different. The expansion rate is different. So they've expanded by 10 centimeters. If they did that in 2 hours, well, that's 5 centimeters per hour. That's more than twice as fast as the nearer raisins moved. So it's interesting to think about that a galaxy that's farther away from you would be moving away faster if the universe is expanding, because there's more space between you. The more space there is, the faster the expansion. This is a great analogy. The great thing about it is you can imagine the raisins inside the dough. It makes it a three-dimensional model. The raisins on the backside of the dough as well. Try to imagine that all of them are getting farther apart. However, the raisins themselves aren't growing. They're staying the same size. It's just the distance between them as the dough expands is getting greater. So in the raisin bread dough analogy, obviously the raisins represent your typical galaxy, okay, or you could say clusters of galaxies would make it even better. And then the dough itself would just be the emptiness of intergalactic space, empty space. So each raisin moves away from every other raisin in the dough. The farther apart they are, the faster they move apart. That's basically Edwin Hubble's law. The farther, the faster. The farther apart you are, the faster you move away. Now keep in mind that this would appear this way no matter which raisin you were on. It would look like all the raisins are moving away from you. The only flaw in this analogy is that the bread has a surface. So that doesn't really correspond to something in the universe. So if that bread dough just kept going and going, it would be a very good analogy. So that is the end of the notes on the universe for now, and we will continue with things that are smaller, because really anything is smaller than the universe.